For this video, we will briefly cover notation for composite functions. Then we're going to start moving on to transformations, which will take up a large chunk of time, probably the most amount of time for all these videos, but let's get to it. So let's say we have a red function. We'll call that f of x. So red is f of x, and the blue function we'll call as g of x. So you're going to see this type of notation for composite functions. And what this actually is f of g of 1. So this over here is actually inside the outer f. I don't know why this notation came to be, but I guess it's just to save space and maybe to cause less confusion, although to me it's pretty confusing. So all we have to do is take the g of 1, put it inside the f, like I said earlier, and we can do this slowly. So let's go find what g of 1 is. Now, when the g value is 1, okay, the x value of g is 1, the y value of g is negative 3. So we know that g of 1 is equal to negative 3, meaning that instead of doing f of g of 1, this is f of negative 3. Now what's f of negative 3? This is f, and the value at negative 1, 2, 3 is 1. And there you go. We can go ahead and do g of 5, which is the same thing as saying g of 5. So let's do what g of 5 is first. 1, 2, 3, 4, 5. G of 5 is 1. So this is the same thing as g of 1 because 1 and g of 5 are the same thing. So I'll take the 1 and replace that. G of 1 is just negative 3. So that is a very brief lesson on the new notation, but all in all, that's pretty much what you need to do. Nothing too difficult. Let's go ahead and move on to transformations. All right, before we do transformations, I do want to go over several functions that will be really important to you, so we can kind of play around with these as we learn how to do movement of graphs. We all know f of x is equal to x. This is the same thing as y is equal to x, the y is equal to x graph. Okay. So if I were to put a table x and y over here like this, okay, let's say I have negative 3, negative 2, negative 1, 0, 1, 2, 3. What this means is if I plug in negative 3 into the x, what will my y value be? F of negative 3 is just negative 3. If I plug in negative 2, okay, then my y value is just negative 2. If I plug in negative 1, then f of negative 1, which also stands for y, by the way, is just equal to negative 1. And you see, whatever I plug into my x, my y value is going to be the exact same thing. So if I start to graph it, negative 3, 3, negative 2, 2, negative 1, 1, 0, 0, 1, 2, 3, like that, you see that if I keep going lower or I keep going higher, my points will pretty much follow this pattern. And this is what we call the f of x is equal to x graph, or the y equals f of x, y is equal to x graph. Things can get a little bit more complicated when we have something like this. F of x is equal to x squared. Good. So let's say I plug in negative 3, negative 2, negative 1, 0. Let's go down. 1, 2, and 3. If I plug in negative 3 into the x values, then we get 9. Negative 2, if we plug it in, we get 4. And so on, we get 1, 0, and 1, 4, and 9. And if I were to plot this over here, negative 3, 9 is a bit out of my range, but if I do negative 2, 4, I get this. then negative 1, 1, 0, 0, 1, 1, and 2, 4. If I wanted to plug in negative 3, 9, it would be somewhere over here, and then 3, 9 will be somewhere over here. But for the sake of staying inside our graphs, we'll just do this. Okay. And in grade 11, we learned that this thing is called the parabola. Okay, so I'll make this extend out a little bit over here with the arrows going up like that. Now I'm going to skip x cubed and 1 over x for now. I'll do the absolute value of x. And what this absolute value function sign means is that it takes everything inside that's positive and makes it into a positive. And if something inside is already positive, it still remains positive. And you'll learn a lot more about this, especially when we're starting to graph in absolute value functions in calculus. So let's say if you plug in negative 3. The absolute value of negative 3 is just 3. If I plug in negative 2, the absolute value of negative 2 is just 2. Then negative 1 becomes 1. The absolute value of 0 is still 0 because you can't make it any more positive. If you look at the absolute value of positive 1, that's just 1 because it's already positive. So what the absolute value function does, like I said before, is it turns everything inside into a positive if it's a negative. But if the stuff inside is positive already, just leave it as is. So 2 becomes 2, and 3 becomes 3. Once you graph, it looks like this. These are your points that you have designated to be plotted by you. And you can keep going all the way to the left and to the right, as so. Seems like here you have a sharp V. Okay. And there you are. So that's what the absolute value of x looks like. Now let's look at f of x is equal to the square root of x. All right, for this function, I do not want to randomly plug in 1, 2, 3, 4, 5, and 6. And the reason for that is, well, if I plug in 1, the square root of 1 is just 1. Good. But if I plug in 2, the square root of 2 is going to be a really nasty decimal. It's going to be like 1.2 something, I think. So we want to strategically pick points to actually plug into x to give us really nice y values. So I'm going to actually restart this. Whoops. The easiest number you can plug into a square root sign, is 0. Because the square root of 0 is 0. Then if we have 1, we get 1. And the next number that we plug in to get a very good y value is 4. Square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4, and so on and so on. But I pick these numbers because it's actually really nice to graph. 0, 0. 1, 1, 4, 2. I'm out of space for 9, 3, but there you are. And oops, you have a parabola, or half of a parabola looks like this. Now, I'm going to go through x cubed and how to properly graph that. Okay. This is going to be a little bit more complex because you have to understand what happens when we plug in a decimal very, very close to 0 or 1. If we look at the x and the y values, there are 3 numbers that are extremely easy to plot. If I plug in 0, I get 0. If I plug in negative 1, I get negative 1, and if I plug in 1, I get 1. But every other number that you plug in, you're going to start to run into some problems. If you plug in 2, you get 8, negative 2, negative 8. And why some of these can be problematic is because the numbers get big really quickly. If you plug in 3, you get 27, negative 3, negative 27, because we're using this. These last 4 are going to be hard to plot. So let me go ahead and plot the first three. 0, 0, 1, 1, negative 1, 1. If we really wanted to do 2 and 8, 2, 1, 2, 3, 4, 5, 6, 7, 8, somewhere here. And then negative 2 is 1, 2, 3, 4, 5, 6, 7, and 8. There. But we don't just connect them by using straight lines like that. Because what it actually looks like is something like this. Okay. Oops. Let me just fix this point here. There. Okay. Something like that. So how do we get this shape? Well, the only way to really get this shape, and we can leave this as an exercise for you, is what happens if you start plotting numbers very close to 0? So let's say you plug in numbers like 0.1, then you get 0.001 for your y value. If you plug in 0.5, that gives you 0.625. 125. You can keep plugging numbers 0.6, you get, I think, 0.216. But whenever you start putting these x's into the y's and then starting to plot them, they take on this shape and this shape. And same thing if you go outside of the realm of ones, so 1.1, 1.2, 1.3, it takes that shape. And if you took pre-calculus 12, you have a more in-depth understanding of why these shapes look like this. And the very last thing, f of x is equal to 1 over x. So if we plug in x, if we plug in y, very similar to the x cubed graph, you're not going to really like what you see. So first, if you plug in 0, you cannot have 1 over 0, so it does not exist. If you plug in 1, 1 over 1 is 1. If you plug in negative 1, 1 over negative 1 is negative 1. So there's technically only 2 points you can plug for now. Here. Oops, and here. Okay, if you start plugging in as many points as possible, let's say you want to plug in 0.5 or 0.3 or negative 0.4, and you just plug them into here. Or if you want to plug in negative 2, negative 3, negative 4, or the positives of each, what you're going to have is a function that looks like this. And I'm not going to go over each and every single individual point, but you should get this. Same thing over here. On the left, if you start plugging in points that are very, very close to 1 or very close to 0, or just go on and on and on and on, you're going to get something like this. Remember in the beginning that we cannot plug in 0. No matter what happens, x cannot equal to 0. Because if you do, it just doesn't make sense. So we call this point a vertical asymptote. Because no matter what happens, your x values can never approach this number. So vertical asymptote. So because x cannot be 0, we're just saying that x is equal to 0 for the vertical asymptote. Whatever x cannot be, that becomes your vertical asymptote. Now I want you to focus on 1 over x. If I plug in a very, very big number, if I plug in 10, that becomes 0.1. If I plug in 100, that becomes 0.01. If I plug in 1,000, it becomes 0.001. And no matter what number you plug in, okay, it's always going to get very, 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 very small, but it will never hit 0. You can plug in 10,000, 20,000, 30,000, 1 over whatever that big number is. It'll be very, very minuscule, but it will never hit 0, which is what we're trying to show with this, with this over here. So the number that if you plug in like a really big number to the bottom to, let me say that again. You can plug in a really big number, so like even infinity or even negative infinity. 1 over negative infinity. You'll never hit 0. So these numbers, they approach either 0 or, they approach 0. And this is what we call a horizontal asymptote. A horizontal asymptote happens if you plug in a very, very large number, or very, very very large number that's negative, or a large number that's positive. And whatever that approaches to becomes your horizontal asymptote, which tells us that no matter what happens, your y value will never reach this. So if we focus over here, if you plug in a 10 million, 20 million, 300 billion, whatever, you'll never hit 0. Same thing if you plug in negative 10 million or whatever, you'll never hit 0. So that's what we call a vertical asymptote. And sorry, you'll never hit 0 for the y value. So have a good look at all these functions over here. Okay, you can pause the video, you can rewatch them, rewind them, and watch them again. Do whatever you want, because now we're going to go into the meat of the topic, which is transformations. Y is equal to f of x minus a plus b. Okay. For this one, for the a value, if the a is positive, that means we shift to the right. We'll just say shift to the right for now. And if a is negative, we shift left. If b is positive, we shift up. And if b is negative, shift down.